Okay, so in the last video we started talking about the concept of free fall, which is when an object is falling only under the influence of gravity and there's no air resistance or anything like that. If you have a situation with free fall, then on Earth the acceleration due to gravity has a value of about 10 meters per second squared, meaning an object in free fall, regardless of its mass and regardless of its size, as long as there's no air resistance, is going to have a constant downward acceleration of about 10 meters per second squared. Now, in actuality, it's more like 9.81 meters per second squared, and it actually changes at different locations on the Earth. But for this class, just for simplification, we're going to use 10 meters per second squared for the acceleration due to gravity value. Okay, and we're going to do calculations with that today. So we talked about that in the last class. We talked about the difference between objects that are just in free fall normally, falling straight down or going up or down. We also talked about projectiles, which we'll talk about in the next video. And basically, again, a projectile is an object that's falling in two dimensions, where not only is it falling down, but it's also moving horizontally. And so in this image here, you can see that the ball that's in red is just falling straight down. This yellow ball over here is a projectile. Okay. Okay, we talked about the constant acceleration equations and kind of how they apply for objects in free fall, but we're not going to use all of these equations for the problems we're going to be doing. Okay, so we're actually going to simplify a bit. So we left off in the last video talking about example 0.25. We went over that in the last example. So let's start with kind of a review example. So this is example 0.5. So see if you can answer this question based off of what you learned in the last video. So the question says, which of the following is not true about an object that is dropped in free fall? Okay, so based off of what you learned in the last video, you should be able to identify which of these is not true. 3 of these statements are true, but 1 of them is not. So see if you can figure that out. Okay, so let's talk about this. It says, which of the following is not true about an object that is dropped in free fall? So answer choice A says you can ignore air resistance. An object that is in free fall, by definition, the only thing acting on it is gravity. Okay, remember we saw the video on the moon where the hammer and the feather hit the ground at the same time, and the reason that they would not hit the same time on Earth unless you removed all the air is because of air resistance. So situations involving free fall automatically ignore air resistance. Okay, so A is a true statement. B says the initial velocity of the object is 0. So think if you drop an object, okay, so let's say you hold like a ball or something in your hand, before you let it go, it's not moving. Okay, it's at rest, meaning its velocity is 0. So that means when you drop it, as it leaves your hand, the initial velocity is going to be 0 because it wasn't moving before you let it go. So B is also a true statement. C says the acceleration of the object is constant. That's definitely a true statement. That's like the whole concept of free fall, is that if you have a free fall situation, all objects, regardless of their mass, have a constant downward acceleration due to gravity. And that's that G. That's that negative 10 meters per second squared that we talked about in the last video. Okay, so the correct answer is D. The velocity of the object is constant. There's no possible way that could be true for an object in free fall, because if it's accelerating, that means its velocity can't be constant, because acceleration is how fast your velocity is changing. Okay, so the acceleration due to gravity, negative 10 meters per second squared, that means for a falling object, every 1 second, the velocity changes by negative 10 meters per second. Okay, so velocity is definitely not constant for an object in free fall. Okay, so that was a little concept question. So let's move on and do some calculations. All right, now I said before that basically the equations that apply for free fall look very similar to the equations that we had for constant acceleration, except instead of the delta x's, we replace them with delta y's, because now the displacement is up and down rather than side to side. And rather than the a, you have g, which is the acceleration due to gravity. G is not gravity, it's the acceleration due to gravity. Okay, so it's still an acceleration. So in these equations, we've just replaced a with g. Now, for simplification, based off of the problems we're going to have to do for this class, we're not going to use all of these. In fact, we're only going to be dealing with situations where an object is being dropped from rest. Okay, and so because we're only going to be doing problems where an object is being dropped from rest, we're going to simplify down from 3 equations down to 1. Okay, so the equation we're going to use for objects in freefall is just this one right here. Okay, it's delta y equals 1/2 g times t squared. Okay, and the reason we're using this equation, again, is because if an object is dropped, the initial velocity is 0. And so this equation kind of simplifies down to what you see on the screen right now. Now, I do want to point out that g is a constant. Okay, remember the acceleration due to gravity, that's that little g, that's negative 10 meters per second squared. We're going to use that throughout the year. Okay, so you'll see that again and again. Time, of course, is in seconds. And then delta y. Okay, so we have delta x and delta y. Delta y is what we call vertical displacement. And when I say vertical displacement, vertical I mean up and down. Okay, so up until now we've been doing problems with, cars and toy trains and stuff like that. Objects moving side to side, horizontally, we would say. Okay, and so there's 2 types of displacement, and we'll see delta x again when we talk about projectile motion. But delta x is usually used for horizontal displacement. But since we're talking about falling objects, falling up and down, we put delta y. Okay, so just think, it's easy to remember if you just think like from math, you have y values that go up and down, and then you have x values that go side to side. Okay, so delta y is basically, it's displacement, but it's up and down displacement. Now, I also want to remind you of a few things before we do some examples. Number 1, remember that all objects in freefall have a constant acceleration. That means a non-changing acceleration. Also remember that if you have an object that is falling down, then the displacement, delta y, is going to be negative, because down is the negative direction. Okay, and finally, I said this before, but for falling object, the y velocity is changing. It's decreasing by negative 10 meters per second each second because of the acceleration due to gravity. Okay, so keep those things in mind, and we're going to be using this one equation to be solving problems. So if you need to write this down in your notes, okay, we're going to be using it in all the examples and on the practice worksheet that you're going to be working on. Okay, so pause it there if you need to write that down, and then we'll do some examples. Okay, so let's take a look at example 1. Okay, so example 1 says, Anna dropped a rock from the top of a 60-meter high bridge. I can't draw a bridge, but I'll draw like a cliff or something. So let's say here's Anna. Okay, and she has a rock, and she's standing on top of a bridge that's 60 meters high. It says ignoring air resistance. So if there's no air resistance, that means we have a situation with free fall. The question says how long. Okay, so as you're reading these questions, you should be identifying your givens and your unknowns. Okay, so first of all, this is an unknown question. How long is always about time, right? So before I go to find my givens, number 1, if it's being dropped, of course, the initial velocity is 0. If it's being dropped off of a 60-meter high bridge, that means that it's going to fall 60 meters. Okay, and so my vertical displacement, my delta y, is going to be 60 meters, but it's a negative 60 meters because it's falling down. Okay, now also you always have g for objects in free fall, that's negative 10 meters per second squared. My unknown is time, and we're only going to be using the one equation for these free fall problems, that's delta y equals 1/2 gt squared. And now all I need to do is plug in and solve, substitute and solve. Okay, delta y is negative 60. That's equal to 1/2 times g, which is negative 10. So now g is not a variable, that's a constant. Keep that in mind. And then times t squared. Okay, so before I go to solve, I'm going to simplify because I can combine the 1/2 times negative 10 is negative 5. And so now I ask, what is being done to t squared? Well, number 1, it's being squared. And number 2, it's being multiplied by negative 5. Okay, so I need to undo these things, and I need to think SADMEP, PEMDAS backwards. Okay, I don't have anything to subtract, I don't have anything to add, I don't have anything to multiply, but I can divide by negative 5, and because dividing by negative 5 is going to undo multiplied by negative 5. Okay, so notice how the negative 60 divided by the negative 5, notice how those negative signs cancel out. Okay, so negative 60 divided by negative 5 is 12. And then I still have to undo that squared. And remember that the opposite mathematical operation of squared is the square root. So now what I want to do for my last step is I want to take the square root on both sides. And so I do that in my calculator. I take the square root of 12 and I get 3.46 seconds. If you ever are trying to take the square root of a negative number, that means you missed something. Okay, that probably means that you didn't make delta y negative like it should be. Okay, so if your calculator ever says like no real solutions, that's because you're trying to take the square root of a negative number and you can't do that. Okay, so that's how you would answer question 1, or example 1. Okay, so pause it there if you need to look at that some more. Okay, so let's take a look at a few more examples. So example 2 says a small boy drops his toy car into a well and hears a splash 2 seconds later. So right away I have time as a given, that's 2 seconds, and I always have g as a given for objects in free fall. That's negative 10 meters per second squared. Now my unknown, it says approximately how high. So how high is kind of like how far. We want to know how high is the well. So we're kind of asked about delta y. Now I say kind of asked about delta y is because if I ask you how high the well is, I'm kind of expecting you to give me a positive answer. But when we go to use this equation to calculate delta y, we're actually going to get a negative answer. Okay. And the reason for that is because delta y, the vertical displacement is negative because the toy car is falling down, but answers about height should always be positive. So again, we only have the one equation that we're using right now. Okay, so we don't have to worry about picking and choosing equations. Delta y is my unknown, and now all I need to do is plug in. Okay, so I don't even need to do any rearranging to solve this. I just multiply these things. 2 squared is 4. 4 times negative 10 is negative 40. And then half of that is negative 20. Okay, so my vertical displacement, my delta y is negative 20 meters. Now, how high is the well? Height cannot be negative. The displacement is negative, but height cannot be negative. So the answer to the question would just be 20 meters. It's a positive 20 meters. Okay, so we're using the vertical displacement to find the height. It's the same number, but you're just ignoring the negative sign because you cannot have negative height. Okay, so that is example 2. So pause it there if you need to look at that some more. Okay, a couple more examples. Okay, example 3 says a textbook is dropped off the roof of a school building. If it takes the book 3 seconds, there's that time. T equals 3 seconds. If it takes the book 3 seconds to hit the ground, I always have the acceleration due to gravity. Again, that's not gravity, it's the acceleration due to gravity. I always have that as a given. My unknown is height. Assume that the textbook is in free fall, so no air resistance. Okay, so once again, this is basically the exact same situation as example 2. Okay, so it's really not any different. Alright, so what I want you to do is see if you can answer example 3. So pause it here, see if you can get an answer to this question. Okay, so from here we're just plugging into the equation. Delta y equals 1/2 times -10 times t squared, so times 3 squared. Okay, so 3 squared is 9. 9 times -10 is -90, and then half of that is -45 meters. Okay, so the answer to the question is the height of the school building is 45 meters. Remember, you cannot have negative height. So the delta y is -45. That just means it goes down 45 meters. That's because the height of the school building is 45 meters. Okay, so that is example 3. Okay, so pause there if you need to look at that some more. And then just one more quick concept example. You throw a ball straight up into the air at the highest point. See if you can answer this question. Okay, ball goes straight up into the air, and at the maximum height of the ball, at the ball's highest point, right before it starts to fall back down. See if you can answer this question. Okay, so the answer to this question is C. Remember, object in free fall has a constant acceleration. That means it does not change. That means it doesn't matter if it's going up, it doesn't matter if it's going down, it doesn't matter if it's at the highest point. The acceleration due to gravity is -10 meters per second squared. Okay, that doesn't change. What does change is the velocity. And so at the ball's highest point, the velocity actually becomes 0. And the reason for that is at the highest point, it stops moving. Okay, so imagine that in your head. You throw something up at the highest point, it stops moving for just a split second, and then it changes direction and starts to fall back down. And the reason it stops moving at the highest point is, well, if it was still moving up at the highest point, then it would have kept moving up. Okay, and then it wouldn't be the highest point anymore. Okay, but the acceleration is definitely not 0. Alright, and the very last thing I want to show you guys is not really an example, but something we talked about in the last unit about motion graphs, about what position time graphs and velocity time graphs look like. Okay, so I just want to kind of sketch this for you. It says to graph the position time graphs and velocity time graphs for an object tossed up into the air and falling back down. Okay, this is a situation, by the way, where you need to make sure that you understand that what the graph looks like does not necessarily tell you what the object is actually doing. Okay, so for example, in a free fall situation, we have constant acceleration. It's constant acceleration up and down, but it's still constant acceleration. And in the last unit, we talked about what a position time graph looks like if you have constant acceleration. It looks like a parabola. So in the case of an object being tossed up into the air and then falling back down, the position time graph kind of looks like what you would expect. It does look like a parabola, and it looks something like this. A object goes up, reaches its highest point. This should be a perfect parabola. It looks kind of danky because I can't draw. But it goes up, reaches a maximum height, and then it falls back down. Now, what does the velocity time graph look like? Well, now you need to be careful, okay? Because the velocity time graph looks completely different. Remember that if you have constant acceleration, a velocity time graph is linear, okay? Also remember that on a velocity time graph, the slope represents acceleration, and the acceleration here is -10 meters per second squared. Okay, so our graph should have a negative constant slope, and it should be linear. And so the velocity time graph is actually going to look something like this. Okay, and you might think it's kind of strange that the graph looks like that because the object is going up and then coming down. But remember, what the graph looks like does not necessarily represent the actual motion of the object, because this is not a graph showing you how the object is moving. This is a graph showing you how the velocity of the object changes. Okay, so if you think about it, when the velocity is positive, the object is going up. Notice how the velocity is positive, 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 but it's decreasing. Right here, this is the velocity equal to 0. This is where the object is at rest because the velocity is equal to 0. And so that is where it actually reaches the highest point. And then after that, look at what happens to the velocity. The values become negative. Okay, they become negative because now the object is falling back down. Okay, so you need to think of it like that. So that's just kind of applying what we learned in the last unit about motion graphs to objects in freefall. Okay, so after watching this video, you should be able to solve very basic freefall problems. Okay, and you should also understand the concepts behind freefall, that is the constant acceleration equation, and be able to connect that to things we've talked about in the past. As always, please let me know if you have any questions, and I'll see you guys in the next video.